Good afternoon, everybody, and thank you for joining us. So we'll just go through a short webinar today on FRED for physical optics modeling, modeling laser systems, and we'll just give a brief overview of how FRED does this, what it's able to do, and a couple of examples. Before we get started, though, I just want to spend a couple of minutes just introducing ourselves for those of us on this webinar today who are not very familiar with us. CBS Europe is the photon engineering's FRED in Europe, as well as Canada and Japan. We sell and provide technical support and training for FRED users across Europe, except Benelux, Spain, and Portugal. And we have staff in 3 countries, UK, Canada, and Japan. And we've been working with photon engineering for 12, 13 years. And a little bit about photon engineering themselves. They're a company from Tucson, Arizona. They were formed in 1997, so they're 25 years old, and FRED, the software itself, I believe is 22 years old. It was first released in 2000 or 2001. So it's quite a mature product, and it's used for a variety of different applications. So very briefly, again, for some of us on this webinar who perhaps have not used FRED before, I know we have a mix of attendees who are FRED users, but also people who are learning about FRED a little bit. Before we do that, though, my name is Tom Davies, COO of CBS, and I've been working with photon engineering for 10, 12 years, and I'm responsible for a lot of the FRED technical support and training. You might have emailed me or called me, or actually been in a class if you've attended one of the FRED tutorials. I've taught the tutorials in Europe and also down in Tucson. So what is FRED? FRED is essentially, it is a comprehensive general purpose optical mechanical ray tracing tool. It's used for stray light analysis. In the aerospace industry, it's very popular, especially in the US aerospace industry. But it's also capable for coherent beam propagation. And I've highlighted that to show you that's what we're talking about today. It's also suitable for a variety of different things, such as imaging, systems analysis, illumination, system design, virtual prototyping, and other things such as thermal self-emission, tolerancing, etc. It is a ray tracing software that is both sequential and non-sequential. By default, the ray trace algorithm is non-sequential, but it does have sequential modes if that is suitable for your needs. It has a multivariable optimization capability, and the higher level of FRED called FRED MBC is a GPU ray tracing version that actually does the ray trace on the GPUs, ensuring that we have simulations orders of magnitude faster than anything else. But today's topic is coherent ray tracing, or physical optics. And I just want to outline very briefly what FRED does, and I think that will clear up the algorithm there. But first, for those of us who are slightly aware what physical optics is, let's just have a quick brief definition. Physical optics, or wave optics, is the branch of optics that deals with things like coherence, diffraction, interference, and polarization. Essentially, these are the phenomena for which the ray approximation of geometrical optics is not valid. And in this context, the topic today, it is the middle ground between geometrical optics, which ignores the wave effects, and the rigorous electromagnetic theory in quantum optics, where you're solving, for example, Maxwell's equations rigorously and doing a field propagation analysis. So we're in the middle ground between those two regimes. So what does FRED do? As you know, FRED is a ray tracing software tool. It is a tool that propagates rays geometrically from source to surface to surface to surface. So it's not a tool built for doing something like FTTD or beam propagation methods, which are more essentially rigorous Maxwell solvers. So what does FRED do? it needs to leverage the tools it has. It needs to leverage the ray tracing engine. So it uses an algorithm called Gaussian beam decomposition. And hopefully this diagram and these 3 bullet points explains the overview of what it does. It's a nice, elegant, flexible technique, and it's broken down into 3 stages, essentially. So let's say you've set up a source in your ray tracing software in Fred, and it has an arbitrary field, arbitrary phase, arbitrary profile. What Fred does before it does any sort of propagation through the system, it's going to decompose this, hence the decompose, into a series of small overlapping Gaussian beams. So that's just a mathematical solution. That's just decomposing an arbitrary profile into a series of accumulating small Gaussian beams. And that's what these red lines here indicate on the picture here. So that's step 1. That's just a decomposition. Step 2 is to trace these Gaussian beams through the system. Essentially, instead of tracing a ray through the system, we're tracing a small Gaussian beam. And the way that Fred does that is essentially creating a, for every Gaussian beam, it's decomposed further into a group of rays, tracing along the axis of the Gaussian beam, those divergence angles, and they travel as a set through the system. And they intersect surfaces as rays would. And then when they get to the final location, such as your detector, what Fred does is take that set of rays that represents a single Gaussian beamlet, recreates the Gaussian beamlet, and does that for every set of rays for every Gaussian beamlet, and then does a coherent sum of all of those Gaussian beamlets to get the overall field at the detector. So it's quite a nice, flexible, elegant technique. And just to summarize, we decompose the source into a series of Gaussian beamlets. We trace these beamlets as a series of rays through the system, and then we recombine them and coherently sum on the detector to get the field and the interference effects, diffraction effects, and so on. So that's called Gaussian beam decomposition. It's a very general purpose algorithm, which is a huge merit in its favor. And just to outline some advantages and disadvantages, the strength of this algorithm is that each beamlet is independent of the other beamlets, and it can travel along its own path, and they don't have to travel in a group. So if there's any sort of clipping of the field or partial reflection from partially the beam or so on, that's completely irrelevant. It's a non-sequential algorithm, and you can have multiple beams, multiple parts of the beams going off in different directions, and that has a really flexible nature to it. What we've noticed as well from everyone using this for many years is that it seems to be much more tolerant than other methods of large amounts of aberration, which is obviously some of us are very interested in making sure that the algorithm can handle this. And any type of surface can be ray traced. With the small print essentially saying, as long as there's no discontinuities or very high spatial frequencies of the order of the wavelength. So we can't use this, for example, we can't use this algorithm to model the explicit structure of a surface grating, for example. But for any sort of macroscopic optics, lenses, and so forth, this algorithm is perfectly suitable. The 2 disadvantages that I've listed here are quite simply that modeling diffraction effects at apertures, and for example, a spatial filter, modeling the spatial filter hole, sometimes requires that you need to resynthesize the field into a new set of Gaussian beams. That's an extra couple of steps when you use the software. So that's a little bit annoying, but it's not a fundamental problem. And in full honesty, the Gaussian beam decomposition algorithm can be a little bit slower than other techniques, such as a fast Fourier transform based technique. And that's because each individual beamlet has to be recreated, and then they all have to be coherently summed to attain the complex field. So it might take a few more seconds than other algorithms, for example. But typically, coherent ray tracing, as performed by Fred, is typically not a huge, high-intensity calculation that takes many hours. Typically, you don't need millions and millions of rays, as we touch upon later. Now, the convenience for the user is that one of the key points is of whether you want to do a coherent or an incoherent ray tracing Fred, it really is determined only by the choice of the source. So here we have a very simple example demonstrating that. Here we have an interferometer. We've got the coherent source here on the left side coming into the beam splitter, and the beam splitter splits one path up to the reference mirror and down, and the other path through to the test mirror, back in, and then down to the detector. Using the exact same model and the exact same coatings, ray trace settings, and so forth, the difference from whether we use the coherent source or the incoherent source are very different. When we use the coherent source, we get exactly the interference pattern we expect. A nice fringe pattern there because of the two beams interfering. If, for example, if I use the exact same plane wave source, same aperture, same wavelength, but it was an incoherent version, and Fred has coherent and incoherent versions, this is the result we get. And I hope you can see that through the presentation. It's just a series of dots for each independent ray. Essentially, because incoherent rays, as you might know, is quite simply a delta function, just a dot at an exact point in space. Whereas in the coherent case, all of the rays that you see here in this view here, these red lines of the rays being traced, every ray that you see here in the 3D view is actually a small Gaussian beamlet, as we mentioned, meaning it has a width in space. And it's those Gaussian beamlets that hit the detector and have maybe a small size, and there's quite a few of them, and they all coherently sum. And it's that coherent sum that allows us to understand the interference pattern. And that's what you don't get when using Gaussian beam decomposition with the incoherent case. Well, we don't get it in the incoherent case. So we need to use a coherent source, and then Fred knows behind the scenes for the user. The user doesn't have to do anything else, that we're tracing the rays coherently and taking into account interference and diffraction effects. So I'm just going to go through a couple of the source types in Fred, because there are a variety of options. And it's interesting just to see a couple of points here. So on the left here, we have the list in the Fred user interface of the various coherent source options. And you can see here I've highlighted the plane wave and the point source. Just to get started with the simplest versions we can, some simple settings for the plane wave, 0.5 millimeter semi-aperture, and these samples a grid of 11 by 11 rays or Gaussian beamlets, basically. If we plot the field as it is, one thing to notice here is that this isn't a perfect plane wave that abruptly cuts off at the edge. We've got this sort of gray area at the edge here. And that's actually a slope of the Gaussian beamlet. So for the Gaussian beamlets that are on the edge, as you know, they have a fixed shape, small, but it's actually a gradual slope effect on the edge of the plane wave. If I increase the number of samples so that Gaussian beamlets actually get smaller across the same aperture, this slope edge becomes more abrupt. There's something to be aware of, and it's just a nice demonstration of that there. For the point source, essentially the number of angular samples and the semi-apple determines the grid of rays that's being used. But a key point to understand is that I plotted this on the log scale, and I'm quite zoomed in. I think this is 10 microns by 10 microns window. As you might expect, it's not an exact point source because in the coherent case, it is an area function. As you can see here, it's not a perfect circle, And that's because of the finite resolution of the number of angular samples we're using to create this source. As you increase this, this will tend towards a more perfect ring structure. Now, for laser beams, typically, well, often we want to use some sort of Gaussian source. And there's actually multiple ways to do this in Phred. So I thought I'd just create a table here, just highlighting the various source types we have. And again, looking at the Phred user interface here for the source selections, I've crossed out one for those of you who are Phred users here. This has been, the source called astigmatic Gaussian beam has been retired. It's still available in the menu for people who have them in the old files, but to be honest, we don't recommend you use that. It's been replaced by the laser diode beam source. So the difference between a laser beam and a laser diode beam essentially is the divergence angle. If you have a large waist, low divergence laser beam, so a few millimeters in width or larger, recommend you use the laser beam source. If you have something which is much higher divergence, for example, a laser diode, then you probably use the laser diode beam source. It's more suitable for smaller wastes, large divergence. And the m² laser beam is exactly the same, but has the m² factor for the additional divergence beyond a typical divergence of a Gaussian beam. So it's a good way to choose which source to use, is consider these effects. And then other things like super Gaussians, things like that, you'd use Phred's detailed source type and create your own customized source for that. And just the final slide before we get to actually some Phred demonstrations, just to highlight the differences again between the laser source and the laser diode source. So the laser beam source, which is positioned here in this user interface, is propagating a set of parallel rays to define your Gaussian profile that you defined in the source settings. The laser diode beam source and the m² laser diode beam source actually defines the rays as a set of diverging Gaussian beamlets. So another thing to consider if you are setting up your source in your model, do you want to set a parallel rays passing through your system, or a set of highly divergent rays intersecting with the first optics in your system? It's another thing to consider here, because these, at this surface here, produce pretty much the same Gaussian field, but obviously these geometrical rays that represent Gaussian beamlets are heading off at higher angles, which might affect the number of rays that are actually passing through your system. So let me flip over to the Phred window and give you a couple of examples. This it's a short webinar, so got time for 10 minutes of just showing you the Phred user interface and talking about a few things. So here is a really nice example that we put together with the help of our friends at Optosigma. This is a phase shifting interferometer, and you can see here it's got the optics, but also all of the optomechanical structures and the optical bench. If I do a ray trace, it takes a couple of seconds just to do what it needs to do. Okay, and there you can see the red rays passing through the system and ray tracing, allowing us to collect the interference effect at the detector, which I can show you right here. Plot the irradiance, and there's the interference at the detector after bouncing off the sample, allowing us to understand the surface profile of the sample under test. So even though there's a lot of parts here, and sometimes it's useful to include all of the optical mechanical parts, quite simply, the optics themselves are quite straightforward. There's your source here, you got your mirrors, your lenses, beam splitter, and so on. And then Phred allows you, though, to put everything in a 3D context, which is not only great for visualization, but it allows you to understand if there's any sort of impingement, like your beam is going to clipped by an aperture or diffract or actually get in the way of something and cause scattering or diffraction effects. So, but Phred can certainly handle both the optomechanical and the individual pieces here. Looking at the source itself, quite simply in the source settings, straightforward, it was a Gaussian beam of this waist and this wavelength. And we just put it at the right location at the front of this object that houses the laser. And then we can do the ray trace through the system. This is a really nice example that requires a script to be run to automatically move the spacing of the arm so that we can calculate the phase shift interferometric pattern. And if you're interested in having a look at this example, please let me know after this webinar. Now, for a second, I've got two other very quick examples here, just to show a couple of points I want to show. This here is essentially a laser diode stack. And if I just take the 3D view, cut it in half, so we can look inside. What we have here is a collection of laser sources. Right here, at the moment, only one is traceable. And it's just a laser line focusing on through the lens onto the detector. If I plot the irradiance, we just got the laser line you see here. Now, in the sources folder in Fred, I've got actually 15 sources. Let's set them all to be traceable. So here they are all on the line here. Oh, that's ray trace. Okay. And then let's look again at the irradiance of this location. First of all, though, note that there's no fundamental problem in this algorithm of having multiple sources. So here I've got the same source repeated in multiple locations. Absolutely no problem in Fred. And then they all trace simultaneously. I plot the ray trace, I plot the irradiance, and I get some sort of interference pattern in the Y direction from the interference of all of these laser diodes. Now, one thing I do want to show you, if I plot this on the, if I share this in the 3D view, let's go zoom in, here we are. So the geometrical rays only hit this spot, but we have an interference pattern above and below. So interestingly, this is essentially a demonstration of the fact that each geometrical ray you see here is a Gaussian beam of extended width. And in this case, by the time the Gaussian beams reach this plane here, they're actually quite large because they diverge through space naturally. So the Gaussian beam is probably up to this extent in the Y direction, and they're all overlapping with slightly different angles, positions perhaps. And it's the coherent sum of all of those Gaussian beamlets that produce interference effects up here in this system here. So quite kind of an interesting point to make, demonstration of the fact that when you're using coherent ray tracing in Fred, don't just consider the geometrical rays. These are just the axes of the Gaussian beamlets going through the system, but they all have finite width, and therefore you can see power outside of this region. But I thought that was a nice demonstration of that. Okay, just one final example as well. Again, this is just an introductory topic on physical optics. And then we'll, as we go through this series of webinars, we'll do more specific topics here. But this is the last example I want to show you. It's quite straightforward. Here we have a beam expander. Our source here on the left side, just in this area here, is a 1 millimeter waist Gaussian beam traced through the system. And it expands. And this is actually a magnifying of 4. So if I plot the Gaussian beam on this location here on the surface, we have a Gaussian beam that's approximately a waist of approximately 4 millimeters. Okay, so that's interesting, but that's not what this example is about. It's just what we have on this plane actually is an aperture. I'm just going to set it so we have it now. Let's say an aperture of 2 millimeters by 2 millimeters. And let's say we wanted to understand the amount of power that's passing through this aperture. We can do a ray trace. We can calculate the irradiance passing through. Here's the rays passing through. And then we can repeat for different various of apertures. But one of the strengths of Fred is the built-in scripting language. So I've written a short script here in my embedded scripts folder, where I've just done a loop of various aperture sizes. So a series of 25 calculations where I change the aperture size and I plot the data, just so we can do a quick sort of scan of this information. But first thing, I'm just going to float this and hopefully doesn't disappear. Okay, here we go. Okay, so I'm going to right click, run my script. And you can see here in the 3D view, the aperture is changing. And my script is just dumping the data in the output window where we're dumping the semi-aperture of the aperture. And we're calculating the truncated power passing through the system. So we're truncating this Gaussian beam, and we're understanding as a function of the aperture, the power level, how the power decreases. And Fred automatically plots the graph of this. So for A over W, which is aperture over the waist, so for an aperture size of 8, we get pretty much all of the power through. If the aperture is the same size as the waist, we get approximately 86%. So we can very quickly and easily do these sorts of graphs like this in Fred using the scripting function. And Fred can handle this type of aperture clipping type calculation. Now, one thing to finish this example off, just to make it slightly more interesting, I have a subassembly here called target. I'm going to right click, set it to traceable. And I've just added another lens after the aperture and focus it down onto a target. So let's say for an aperture of 4, so this is the surface settings. I'm just setting the aperture hole size. Let's do a ray trace. And now you can see the part of the beam that passes through, that's truncated, is then focused down on the target. So let's have a look at this irradiance pattern. Choose my analysis service called on target. And quite interestingly, we see, and this is essentially just to preview what we'll talk about in the next webinar. This is obviously a diffraction effect due to the truncation of the Gaussian beam, because this is not a simple cutoff of the Gaussian beam. We've got essentially a diffraction effect, a near focus diffraction effect, which would change as per the aperture. But the key message to point out here is that Fred handles diffraction inherently. So there was nothing special I had to do about switching on the diffraction calculation or anything like that. This happens naturally in the Gaussian beam method. The only requirement for you is that you need to spatially sample the aperture as well as you can with the small Gaussian beamlets. But if you do that, you will naturally see diffraction and interference effects. And that's one of the key benefits of using Fred for coherent ray tracing, is that quite simply, you don't have to do anything special to worry about diffraction, interference, and things like that. So that was a couple of quite introductory examples. I do appreciate they're quite simple, straightforward, and just sort of overview of Fred for coherent ray tracing. As we go through this webinar series, and the next one will be scheduled shortly in a couple of weeks, we'll focus on more specific topics and we'll have more specific examples. But this was just an introduction of to overview what Fred does for coherent ray tracing, and just quick summary. Fred uses a technique called Gaussian beam decomposition, which allows us to leverage the ray trace engine that is already inside Fred. It's a flexible technique that's inherently non-sequential. And the choice of source, whether you use a coherent source or an incoherent, determines if the beam is coherent. Multiple coherent source types and diffraction and interference effects are automatically included in the calculation. And Fred's scripting environment makes automation and tolerancing and things like that incredibly easy. So that was just, I think my time is up. I just want to say that we're doing another one of these webinars, again, another half-hour webinar in 2 weeks from now on November the 10th at 3 p.m. CET. And in that topic, I'm going to focus specifically on diffraction effects. So we're going to talk about how Fred can model Fraunhofer diffraction, Fresnel diffraction, and near-field diffraction, followed by an example or two on these matters here, including how it determines image quality in a couple of cases. So that will be in a couple of weeks, and we'll send out a notification for this. And I hope that you join and find the topic valuable. And of course, if there's any topics related to physical optics that you're interested in hearing, let us know, and we'll try and accommodate it. So that's the webinar, next one coming up in 2 weeks. I also want to take a moment to mention that if this is a topic that's absolutely critical for you in your work, we have a 3-day training course on physical optics modeling in Fred. And we're hosting this at the end of November, November 29th to December 1st. It's a 3-day course, it's online. And you'll find on the website an itinerary, an outline of the course contents, and a way to register if you're interested in that. So again, if this is critical for you, that could be something interesting for you to think about. So I'd just like to thank you for your time. Further information you can find out at the website. You could email us, or you can, if you're a Fred user who likes to find answers to simulation questions, you go to the Photon Engineering Knowledge Base as well, which is a wonderful resource as well. So that's the end of the webinar. Please, if you have any questions for a Q&A, please jump into the chat and I'll answer what I can. If not, thank you for attending, and hope to see you again in a couple of weeks. A couple of questions that have come up. Okay. Are there any built-in checks to ensure apertures are adequately sampled? No. So that's something that you do have to keep in mind if you're tracing through an aperture, is to understand for yourself the quality of the beamlets passing through. They have to be adequately spatially sampled, and they have to be reasonably finite in size. Gaussian beamlets, as they travel through the system, they expand. So if they reach your aperture and they're already expanded so they're the same size as the aperture, you're not going to get an accurate representation of that hard cutoff of the aperture. So one thing to do is to stop the rays at that location. And there's a tool there where you can plot the waste of all these Gaussian beamlets, and you can double check for yourself if you think that's suitable. If not, then there's a process called resampling where you generate a new set of rays to continue the propagation. But it's not automatic. So that's something you have to be aware of, which is a topic we'll cover when we talk more about diffraction in the next webinar. But certainly that is something that is a key question you need to ask yourself. If you have smallish apertures, you have to make sure they're well spatially sampled. A question about the physical optics course. Is it suitable for Fred beginners who have experience with perhaps other software? Possibly not. It's not a tutorial on how to use Fred as if you've never sat in front of Fred before. It assumes you are reasonably competent in using Fred and have used it already for your work. There's no real build up in learning how to add a source or add a lens or position it properly. That's all assumed that you are already an expert at, or comfortable doing anyway. So that's something to be aware of. If you have any doubts, get in touch with us, and we'll maybe get together on a quick web meeting just to see how comfortable you are using Fred. Obviously, we'd like you to attend the course if it's valuable for you, but it's only valuable if you can speed through the examples and the content without struggling with the basic operation of Fred. So get in touch if that's a concern of yours. A couple more questions. Okay, what incoherent sources can you use in Fred? So just briefly touching upon the incoherent sources. There's a collection of incoherent sources. plane waves, point sources, converting a surface into a Lambertian emitter, a volume point source. And then you have the freedom, these are all the standard defaults, but you have the freedom to create your own using what's called the detailed source dialog. And that can allow you to really customize the ray positions, the ray directions, the apodization spatially and angularly to really create your own customized source. But all of the typical ones, source types are, I would expect to be available. Laser diode, incoherent LED sources, laser diode sources, things like that are also available. Okay, I think that's about all of that. But if there's any more questions, let me know. Otherwise, we'll close the webinar, and I hope to see you again in a couple of weeks. So again, thank you for your time, and we'll leave it there, and I hope to see you again. Thanks.